Hello, ladies and gentlemen. Hey, this is going to be a lecture on center of mass. Now, a center of mass in physics is a little more complicated, but as we move into greater complexity into the world, we need more complex ways to describe it, and that's where we're headed to next. Now, one way that we need to know the center of mass, for example, is if I throw this object and I throw it through the air, it might travel like this. Now, what we talked about before, when we throw something, it would follow a parabolic curve. Now, that is true. So the center of mass of this object, even if I throw it and twist it, the center of mass is going to follow that parabolic curve. But if we want to center on a space outside that center of mass, we would need to know where that center of mass is to describe things that are going on outside that. Okay, so anyways, there's lots of applications of this, and that very often comes up when it comes to rotational kinematics, which is what the chapter we are going to next. But regardless, with this center of mass, in this first case, in a regular geometric object, the center of mass, okay, the center of mass is in the geometric center, So if we take something like this regular meter stick, okay, and we balance it on our hands here, it is going to balance in the exact middle, okay? And if we hang it straight up and down, we can draw an imaginary line that goes down through the center of mass, and we could do the same thing here. So where all three of those lines are going to intersect would be the center of mass of that regular object. And we could just call it, at least in this direction, we just call it halfway. If we take something like a, let's say a book is kind of a regular object, the density is the same. Usually when we talk about regular, we're talking about uniform density. But regardless, if aside from the fact that the cover is a little bit different than the outside, the center of mass of this would essentially be half the length, half the width, and half the thickness, and we'd find that spot, and that would be the center of mass. So regular objects, regular geometric objects, the center of mass is in the geometric center. Well, we could have something that's not so regular, and we can figure this out for kind of that same reason. If I take this this golf club here, and I could essentially balance it on my finger there, and then the center of mass would go through there. But we're going to concentrate more on regular geometric figures to begin with. Now, you guys, that should seem somewhat obvious, but what if we have an irregular object, or sort of a regular object, but that is kind of in an odd shape, okay? In that case, we're going to use the following equation. The example that's going to follow this will make a lot more sense, which we'll use this first part. Okay, so to calculate the center of mass, let's say in the x direction, we can do it in the y direction, z direction, is going to be x1, m1 plus x2, m2, x2, m2 plus x3, m3, and that would continue on depending on how many objects we would have. And that would be divided by m1 plus m2 plus m3. And again, depending on how many objects we had. Now, this right here, okay, would also equal the total mass. We can also see then, since we have a mass in the denominator and a mass in the denominator and a mass in the numerator, they're going to cancel out. So our answer is going to be in whatever units that we have. So in the x direction, it would probably be meters, but we can make it centimeters, feet, yards, miles, whatever unit that we have for length. All right, so here is an example that we're going to use, which is essentially the culmination of several sort of regular objects. Now, assuming that the uniform is density and we're going to have a common thickness, we're going to assume that each block, is going to have the same mass because it has the same density. And this, you guys, this would be much harder to determine where the center of mass is, unlike a rectangular prism, for example, which would be in the exact middle. All right, so what we're going to do in this case is we're going to break this object into 3 rectangular prisms. Okay, so we're going to take this first one right here, and we're going to call that M1. And then we're going to take this upper part right here, we're going to call that M2. And finally, we're going to take this bottom part, and that's going to be M3. So this whole area is going to represent M3, whereas this whole area is going to represent M2. And then finally, we're going to have all that red area is going to resemble or represent M1. Now, we essentially are ignoring that depth there, but since the depth is constant for all of these, the center of mass as far as the z direction goes would just be a half. If this width is 1, then the center of mass would be a half. Okay, so now we're going to take our equation, and we're going to say x center of mass is equal to x1 m1 plus x2 m2 plus x3 m3. And now we only have 3 objects here, so we're essentially done here, which is going to be m1 plus m2 plus m3, which is going to be our total mass, All right, so now we need to ask ourselves, in the x direction, where is the center of mass? Where is the center of mass of M1? Now, since we have this 4 cubes here, but in the x direction, we can see if this length is 1, etc., then our center of mass would be somewhere along the middle. So in the x direction, that would be 0.5. So we're going to put in 0.5. And although we do not know the exact mass of this object, we can see that the mass would be proportional to the area, proportional to the volume, but the depth is the same. So it's going to be proportional to the area as well. And since this stack has 4 cubes, we're going to call the mass 4. Okay, now we can do the same thing. For where's the center of mass? Where's the center mass of M2? Now we know it's going to be right there in the geometric center, right? But when we count in the x direction, that's going to be 1, 2, 3. Half of that is 1.5. So that's going to be 1.5. Its mass is going to be 3. Now, we know that this in this bottom one, we got 1, 2, 3, 4, 5. So we know the center of mass is right there at 2.5, right? But we are measuring kind of from this origin here. So it's going to be 2.5 plus our original 1. So that's going to be 3.5, okay? Our mass is going to be 5, okay? And now all of our blocks together, we're going to have a block of 4, a block of 3, and a block of 5. That's going to give us a total of 12. Okay, so now we can do the math. So we're going to have half of 4 is 2 plus 3 times 1.5. That's 4.5 plus 2 is 6.5. And we're going to have 3.5 times 5 is going to be 17.5 plus 16.5. That's going to be 24. Okay, so that's going to be 24 divided by 12, which is going to equal to 2. So 2 is equal to the center of mass in the x direction. And again, if we wanted to use standard units, then that would be 2 meters. So it would be 2 meters. So in the x direction, our center of mass would be somewhere at the 2 mark. So you guys, Now we're going to do the center of mass in the y direction. We can see the center of mass in the y is this same equation, except we're just substituting x's for y's, okay? And now we can see that all of this, you guys, all of this is going to be the same except for the center of mass. So we're going to essentially erase this. And now when we take a look at the center of mass of our first object in the y direction, this is 4 units high, so our center of mass would be halfway up, which would give us a center of mass of 2, okay? Now, our center of mass in the y direction for our upper one is going to be halfway up, right? But we've got to add that to our original 4, so that's going to be 4.5, okay? And if we go down to this last one, we're only going up a half, okay? So that's going to be 0.5, okay? So now we can redo our calculations. We're going to have 2 times 4 is 8. 3.5 times, or 4.5 times 3 is 13.5 plus 2.5 is going to be 15, and 8 is 23. 23 divided by 12. Okay, it was, see, 4.5. That's 13.5 plus 2.5 is 15 plus 8 is 23. 23 divided by 12 is going to be 1.875. And we're going to call that 1.9. We're going to call that 1.9 meters per our center of mass. So the y center of mass is going to be 1.9. So we can say center of mass would be 2 in the x direction, 1.9 in the y direction, so we could call it 2.0. And then if we wanted to do the z direction, that would be 0.5, and that would be our x, y, and z, our x, y, and z direction. Okay, so you guys, actually pretty straightforward. You just have to be a little bit organized. And you guys can break this up into however you want. So you could make this block number 1, this whole bottom part. You can make this next part, 1, 2, 3, 4, you can make that M2 and make this M3. It doesn't matter how you break that up. But it's pretty straightforward, and you just have to kind of go through that and just make sure you are doing that systematically. And even though I think this is right, I did this in my head, so my calculations might be wrong. So if you calculate this out and you realize I'm wrong, I just screwed up in my head. Okay, so that is going to be our second, you guys, that is going to be our second type of center of mass, which I'm calling kind of the algebraic center, because we're going to do it through algebra. Now, our third type, which is the one that's certainly more interesting, is going to be an irregular object, but having known parameters. If we have an irregular object with known parameters, if that sounds like calculus to you, you are correct. Okay, so our equation for calculating the center of mass, and we're going to start with the x direction. So x center of mass is going to equal to 1 over m times the integral from, let's say, x initial to x final of x dm of x dm. Now, you guys, the calculus aspect in this example, or the next 3 examples that I do, are the algebra. I'm sorry, the calculus couldn't be easier, as you will see. But as in with most word problems, either in calculus or physics, it's not the math that's hard, but it's getting to the math. It's getting to the math that is tricky. So we are going to do example, you guys, we're going to do example 9.1a and b, 9.1a and b, which is in your book, and I believe it starts on page 248. So you guys can review that, and that will help you. And for this first, you guys, for this first problem, we're just going to take a rod, okay? We could think of it as a rectangular prism. And this is going to have a length of L. So we're going to start at 0 and we're going to go to L. It's going to have a mass. It's going to have a mass of M. It's going to have a mass of M. Now, our thickness and our height are going to be the same. Therefore, the only thing that's really changing is we want to know where the center of mass of that is. Now, as you probably pointed out here, is if this is a regular object, then our answer to this question should be right in the middle. It should be right in the middle. And for this first part, I'm going to show you that, in fact, it is right in the middle. And then we will go to something that's a little more complex, and we'll see how that works. Okay, so X, center of mass, is equal to 1 over m times the integral of x dm. So as you know from calculus, this right here is not in a form that you can integrate yet, because we've got x and dm. We need to change these so that they are representing the same variable. And we're going to use that with density. Okay, now we're going to use the Greek letter lambda, and this is going to stand for linear density. Okay, you guys are probably used to having a volumetric density, which is mass over volume. Okay, now this linear density is just going to be mass divided by length. Now, if you think about density here, you can have all kinds of densities. So this would be, for example, kilograms per centimeter or something like that. We could have our charge per area if we wanted to talk about, let's say, static charge on a balloon. So there's lots of different kinds of densities. In the beginning, we are going to use linear density. Okay, so mass over volume, or mass over length, is equal to our density, but we could also, and this gets us to the calculus point of view, we can take a little strip there. We can take a little strip here, and we're going to say that the width of that little strip is equal to dx. So we're essentially dividing this whole rod up into all these dx's. If that's a dx, then this right here is going to be dm. Okay, so now we're going to have dm and dx. So it's the same ratio. Okay, so the change in mass over the change in length is going to be equal to the change in mass over the total mass over the total length, which again is equal to our linear density. So you guys, we're going to come back to this part really at the end of this example. But right now, we're going to say that lambda dx is equal to dm. All right, so we're just going to take this and multiply it over there. So lambda dx is equal to dm. And now we're going to be able to change and substitute that into that position right there. So now we can see that our x center mass is 1 over m times the integral. And now we're going to go from 0 to L. We're going to go that entire length, and that's going to be x lambda dx. So even though we're calling this 0 and L, this is the length, and it is in the x position, the x direction, or in that position. So obviously, this lambda right here is going to be a constant. And so this constant is going to come outside of the integral. And we can say now that this is lambda divided by m times the integral from 0 to L of x dx. All right, I've got a little interruption. I'll be right. All right, sorry about that interruption. So we took our constant and put it out here, and now we're going to have x dx. And now we can see here that we have an integratable expression here because we have x and dx. So obviously this integral essentially couldn't get much easier here. When we take the integral of x dx, it's going to be x squared over 2. Remember, that is x to the first. That value goes up by 1, and then we're going to divide by the added value, hence x squared over 2. Now, you guys, that right there is the indefinite integral. That is the indefinite integral. And we want the definite integral, so we're going to evaluate that from 0 to L. We're going to get that from 0 to L, and therefore, we're going to get L squared over 2 minus 0, L squared 2 minus 0, because this would just be 0 squared over 2, all right? And then this is going to go away. We're going to have our lambda over m times L over 2, x center of mass. Okay, so that looks like we're done, but obviously we already said that the answer to our question should be halfway in the middle. Our answer should be L over 2. And that is why we're going to go back to this density, which is going to be m over L. Okay, so density is equal to m over L, and we're going to substitute m over L all the way back here. Okay, so we're going to have m over L, that is our density, okay, divided by m, and now we're going to get L squared over 2. And we can see that the m's cancel out. We can see one of the L's cancel out, and therefore our x center of mass is equal to L over 2. Just like what we said. All right, I will be right back, and we will do the next example. All right, sorry about that break. All right, so that previous example that I just did was example 911A. All right, so now we're going to do 911B. So very similar, except now we can see in our drawing here that we're going to have a density that changes. We're going to have a density that changes over time or over distance, right? So right here, for example, it might be aluminum. It might be all aluminum, and down here, it might be copper. And so as we move along, each one of these little sections, dm, that is dx wide, is going to have a different mass. But we're still going to have a total mass for the whole thing. Except this side is less dense and this side is more dense. So now we're going to calculate what is the center of mass now that we have this. So again, we're going to use linear density here, but now we're going to say that linear density is alpha x. So in an extreme example, if alpha was just this, it would be 0 density down here, and it would be, let's say, if we had 0.35 for alpha, then 0.35 alpha would be our density down there. So anyways, it's changing, and it's changing with respect to a linear or a uniformly increasing. Okay, now this is still equal to the total mass divided by the total length. It is still equal to dm over dx. So when we start with this integral of 1 over m of x dm, and again, this time we're going from 0 to L, we still need to get dm all by itself. So we're going to say dm is equal to lambda dx, but our lambda is equal to alpha x. So now we're going to get alpha x dx is equal to our dm. So now we can make this equal to 1 over m integral from 0 to L of x alpha x dx. All right. This alpha right here, that alpha right there is going to be a constant, so that can come out. So we can have alpha over m of x squared dx. X times x is x squared. Now, you guys, we are in a position where this is differentiable, okay? We can differentiate it, so it's going to be alpha over m of x cubed over 3 evaluated from 0 to L. And this is going to give us alpha m times L cubed over 3. So our x center of mass is equal to alpha L cubed over m over 3. Okay, now, so we can see that this doesn't seem done. This doesn't seem done, and it's not. And just in the same way that we had to go back, we had to kind of go back and use this time, okay, we are going to substitute back in m. And m is the integral of dm. So we're just going to take from the beginning to the end of dm, and that's going to give us the total mass. Well, we know that dm is equal to alpha x dx, which can then give us, this alpha is a constant, so we're going to say alpha times the integral of x dx from 0 to L, and that is going to give us alpha x squared over 2 from 0 to L. So we're going to have m is equal to alpha L squared over 2. M is equal to alpha squared 2 over alpha L squared over 2. So that is going to go in there, and we're going to get alpha L cubed over 3, and our m is alpha L squared over 2. And now we can see that we're going to get some things that are going to cancel each other out. Our alphas cancel out. L squared was going to cancel out with 2 of the L's up there. This 2 in the denominator of the denominator becomes the numerator. And so our final answer, x center of mass, is going to equal to 2/3 L. And that is our final center of mass if our density is changing in a regular manner across that the length of that tube. All right, you guys, I'm going to set up our next example, which is going to be 912, and I'll be back in a second. All right, ladies and gentlemen, here is our next step. So you guys, this is going to be example 912 in your book, and I think it is on page 249. 249. Now, you guys, it's right after the examples that I just did, which was 911A and 911B. Now, we're going to get a little more complicated here, and this is going to seem confusing, and you just need to go over kind of step by step. And you can do it several times. You can watch this video again, or you can go back and look at the example in the book and see what they do each step. Now, you guys, you can see if you look on page 249, what they have here is an example is if you wanted, for example, to make a sign. This might look like a cheese wheel, and in that example, they call that JJ's Cheese Shop, something like that. Now, if you wanted to hang that sign from only one post or one sort of column, you would probably want to hang that from the center of mass, like this irregular golf club here. So if you were to put a rod up here like this would prevent any stress from going left and right, at least in the absence of any wind or something like that. So knowing where the center of mass is can be very useful. And that is one particular answer. Okay. So now, you guys, we have a triangular prism. We have a triangular prism. It has a base of A, a height of B, and a thickness of T, A, B, T. So obviously our formula for the volume is going to be 1/2 base times height times thickness. Okay, so this time we are going to use a volumetric density, which you might be used to saying density is equal to mass over volume. Typically, physics books are going to use this Greek letter rho, R-H-O, to represent volumetric density. Now, if you saw it as D, that doesn't matter, okay? But in this case, it's going to be our total mass, okay, divided by 1/2 base times height times thickness. 1/2 base times height times thickness, which is the volume there. Now, the other thing we have is we're going to take a little strip out of this, okay, and it is going to have a width of dx, and it is going to have a height of y, and it is going to have a thickness of t, and it is going to have a mass. It is going to have a mass of dm, okay? So when we talk about density here, we can say dm is equal to, now remember, this little slice here is not a rectangular, it's not a triangular prism, it's a rectangular prism, okay? So if we kind of pull this out, we kind of get something like this. So this is going to be dx and y, and then this would be the thickness, okay? So this is going to be dx, y times thickness. So mass divided by volume, okay, are both our linear densities. And again, we might not know what that density is, but it doesn't matter because that's going to end up canceling each other out. So x, center of mass, is equal to 1/m times the integral from 0. In this case, we're going to go from 0 to a, okay, and that is going to be x dm. So just like in the last example, these are not the same variables. We need to change them. So we're going to say that dm is going to equal to rho dxy times thickness, okay? So that is our dm. So we're going to have x rho dxy times thickness, okay, from 0 to a. Now, our density is a constant and our thickness is a constant, okay? So we can pull those out, and we can say density times thickness, actually we're just calling it T for thickness, divided by M times the integral from 0 to a of x, y dx, x, y dx. Okay, so we still have a problem. And our problem is that y is not in terms of x, and that's what we've got to change it to. And this is coming to the next little trick. And if we had a Cartesian plane, okay, and we had a line like so, and if this was A and this would be BB, what would the slope be? And our slope would equal to rise over run. So it would equal to B over A. Now, at the same time, if we took a section right there, okay, then what would the slope right there be? And that would be y over x, y over x. So now we can get terms of y, or get y in terms of x. So bx over a is equal to y. And now we can take this and substitute into our y. So now we're going to have rho t over m times the integral of b over a times x squared, because right here is b over a x times x is x squared dx. Okay, we can also take this b and a are also constants, so that's going to be b over a. So that's going to go outside like so. And now we're going to have the integral from 0 to a of x squared dx, which is going to give us x cubed over 3 times evaluating it from 0 to L, which is going to be L cubed over 3. And we're going to get that rho T B over A M, rho T B over MA. Okay, so obviously that does not look very satisfying. And then we are going to go back. We're going to go back and determine, okay, we're going to determine our mass is equal to the integral of dm, which is going to be the integral of rho dxyt, okay? And we know that y is equal to bx over a. So we're going to have actually thickness will come out of here as well. Let me see, of dx, and our y is b over a x, and that is going to give us rho T B over A times the integral of x dx from 0 to a, which is going to be x squared over 2 evaluated from 0 to a, which is going to give us a squared over 2 times rho T B over a. This a is going to cancel each other out. That is going to equal to m, okay? So now we're going to substitute m here. So we're going to say rho T B L cubed all over 3. And now we're going to substitute this m, which is going to be rho T B A over 2, okay? And again, our rows are going to cancel out, our thickness is going to cancel out, our b is going to cancel out, and we are going to get equal to 2/3 L, this should be a, sorry, 2/3 a cubed, and so I feel like I'm missing something. I think I'll have to go back and you guys can kind of double check that in there, but I think this stays a squared, and so we're going to end up with 2/3 a is equal to x center of mass. And I'm sorry, I lost my train of thought there, but all these interruptions. So we can kind of go back and look at 912, and I will straighten out any misconceptions if I get this. So you guys, it's very important that you kind of go and see this again, and you can go through the book and you can kind of see this. This is also going to be like problem 238 in your problem set for this week. So I will be available for office hours Wednesday, Thursday, Friday from 12. So if you need help with this, we can go over it then. All right, good luck.